All right, as the last people are filing in here, I think we can go ahead and get started. So, hello everyone, once again, I'm Ethan Gutman at the National Center for Atmospheric Research. I'd like to welcome you to the AMS Mountain Meteorology webinar series. I'm going to point out you are all on mute, although you should be able to unmute yourselves if you want to ask questions towards the end. Today we have a special guest with Dave Gochis, also from NCAR, describing, in particular, understanding the NOAA National Water Model and its source meteorologic forcings in complex terrain regions of the United States. The next webinar will be on May 14th with Dave Whiteman presenting on the ice mushrooms on the summits of Patagonia and the meteorology behind them. If you have any trouble during this webinar, please feel free to email me. I'll be checking my email at gutman@ucar.edu, or you should be able to chat in the window in Zoom. This will be recorded and will be available, hopefully not too long after the webinar, although it takes a little time to process it and get everything uploaded. Let's see, anything else? Please hold questions to the end. And for now, I will pass this over to Dave Gochis. See if I can remember how to do that. Go, Dave, you want to take it away?
I think I got it. Put it in presentation mode.
Yep, I see your screen.
Okay, how's that look?
Looks good.
Okay, we'll go ahead and get started then. Thanks, Ethan. Definitely appreciate the invite and the opportunity to talk about this particular configuration that we have of the National Water Model. By that, I mean a chance to talk about some of the meteorological forcing data sets that go into the model. We do give several different high-level talks on the water model between our team at NCAR and folks over at the NOAA Office of Water Prediction about the hydrologic services that come out of the model and a lot of the products that are now being generated at the Operations Center down in Tuscaloosa at the National Water Center. But a lot of times we overlook the meteorological inputs into the model. And of course, those are one of the cornerstones of the ultimate accuracy or not of the model. So it's good to have a chance to talk about those to an engaged meteorological community and maybe stimulate some discussion on what things are working and what things aren't working. So I definitely want to acknowledge a rather large development team within the NOAA Office of Water Prediction, at the Water Center, at their office in Silver Spring, offices in Chanhassen, Minnesota, as well as our group at NCAR that's been working on building a lot of the tools and capabilities we'll go through here today. So much thanks to everybody who's been chipping in for that. So the talk is going to be outlined as such. I'm going to give a really brief introduction to the water model for those who may not be familiar with it yet or have seen some of the sort of other high-level presentations we've given through COASI or some other organizations or conferences. And then we'll take a bit of a deep dive into these forcing data sets that go into it. Really here, the emphasis is going to be on sort of letting everybody know all of the different kinds of meteorological data that are going into it and how we're processing it to get it ready for ingest into the model with huge diversity of data sets with different scales, different time resolutions, different measurement methods that are going into a lot of these data sets. There's a lot of things to consider, and there's a lot of steps that are taken to create sort of seamless, stable data sets, and also some sacrifices that probably have to be made. So we'll talk about what we call this forcing engine, the software code that does all of this in operations, describe some of the components of that forcing engine, particularly the downscaling components, some of the bias correction components, and some recent bias correction work that's going on to try to correct some of the data sets that we use before they go into the actual hydrologic model. Then I'll briefly mention a project we have with folks at the Severe Storms Lab and the NOAA Earth Systems Research Lab, trying to ingest some precipitation type information into the model. And then we'll back out from there and wrap up with some more general presentation of material on model performance in some of the mountain regions that we have, particularly in the Western US, but also just sort of around the country, and then wrap up with some a little bit of discussion on some ongoing work and some areas that need improvement. So I'll just go ahead and get started, planning for about 45 minutes here, leave some time for questions at the end. So starting with some of the strategic goals of the National Water Model, going back to 2016 and 2015, when we first started doing the implementation of the WRF Hydro system for use as the National Water Model, NOAA and its partner agencies set out a series of high-level goals for what this new sort of integrated national forecasting system would create. And really the top-level goals were identified to fill gaps and provide complementary guidance to services that they were already providing, say through the river forecast centers or their weather forecast offices. And those really centered around providing hydrologic or streamflow guidance for underserved locations, so areas that were away from or remote to existing streamflow measurement points, and in areas potentially away from streams as well. Another emphasis is along coastal zones, as we've seen the last couple of years. A lot of different vulnerabilities pop up in coastal areas, which traditionally didn't have a huge service associated with them. There's also a desire to create spatially continuous estimates of forecast of a number of different hydrologic variables, say all the major water cycle components. So instead of just focusing on stream flow, being able to produce a system that had snowpack, soil moisture accounting in a fairly detailed way and with fairly high resolution, of course, channel flows and major reservoir inflows, but then also some aspects of shallow groundwater, evapotranspiration, and then ultimately sort of one of the holy grails of hydrologic prediction is to be able to produce accurate inundation forecasts. There's a desire to integrate the model outputs with other geospatial intelligence and decision support tools. And so that meant sort of modernizing a lot of the data services around the model so that the inputs and outputs from the model would easily integrate into, say, web mapping services or GIS systems for very fast and efficient communication, post-processing, display, and so on. And lastly, there is a goal to move towards a more Earth system oriented model conceptualization, which would integrate with other models that NOAA has as part of its flagship suite of models, particularly the weather and climate models, the aforementioned coastal models, large lake and reservoir systems models, and things like that. So, you know, these were just the high level background service oriented goals as the water model started to get developed and put into operations. And so we always check back and make sure that we're trying to serve these goals well over the long-term evolution of the model. So this slide is from NOAA, and it basically describes that level of service. They are looking to provide a full spectrum hydrologic model that provides complementary guidance. And here you can start to see in the lower left-hand corner the different versions that have been created. So it's been a pretty fast track since things got started in 2015 with the initial implementation of version 1 in 2016. And you can see about once a year, either a minor or a major version upgrade has occurred all the way up until the present. So we're now wrapping up what we call version 2.1 of the model, and it will be handed off to NOAA later this year in 2020 and probably become operational sometime in 2021. And then work on the next version of the model has already begun in its scoping and some of the research behind that model. So another look at that same thing, it's just got a few different bullets on what some of the major enhancements were of each one. You can see a fairly quick pace of development moving here. And also, if you look at the graphic in the lower left-hand corner, the improvement, this is now with respect to hourly stream flow Pearson correlation skill that we've seen over that period of time. So if we use a metric of 0.8, which is a pretty stringent metric to hit for hourly stream flow across the country at a variety of different basins and scales and everything, we've seen very significant improvement in the model over that period. If you look at the full histogram of Pearson correlation values, that has shifted much further to the right than, say, the earliest versions. So a lot of the work that's gone on has been focused on either improving model physics, improving some of these source input data sets into the model. That does include the forcings to the model. Some of this changes over years have changed the domains that the model's implemented on, and also a larger emphasis on model calibration and regionalization of the model parameters from their calibrated basins to the rest of the model domain. So the model domains now are looking like this. We've got a full CONUS implementation. When version 2.1 becomes operational, it will include all of the tributary areas to the Great Lakes. Hawaii became operational in version 2.0 and continue to get improved upon. And then Puerto Rico and the Virgin Islands will become operational in version 2.1 as well. And so this will be really the first time some of these other domains outside of CONUS for Hawaii and Puerto Rico and the Virgin Islands have had sort of a 24/7 hydrologic prediction service stood up for them by NOAA. I'm not going to go through all of these next two wordy slides, but they're going to be here for reference for folks, because I know these presentations live on, but they just give you a sort of a bulleted breakdown of the various changes or improvements that have been made in the last two version upgrades that we've done. This here is version 2.0. These bullets are broken out by configuration, forcing, physics, calibration options, some changes in the underlying hydrofabric, and a similar set of enhancements have been worked on for version 2.1. So lots of activities between sort of the large integrated model development group. Certainly refer back to these at your leisure or with specific questions later on. The last thing I want to mention about sort of the high level arena of building a model like this is that, you know, as a scientist, you like to be able to sit down and sort of start with a clean slate and try to think of what is the absolute best thing you can do to represent processes, improve physical fidelity, characterize uncertainty, and so forth. And I guess the sad fact is that in an operational environment, there's always different trade-offs or sacrifices that get made. So what I've listed here is sort of a bulleted breakdown of what each development cycle looks like, and that's in that sort of top list of bullets. So you can see there's a number of different steps that we go through for each new upgrade of the model. And then in the bottom in the red box are these sort of really high level requirements that we have to hit. And I've been calling these the 5 S's lately: stability, skill, speed, service, and science sort of all have to be met. As one of the director of the Office of Water Prediction likes to say, the value of a perfect forecast is 0 if it comes out too late or if nobody can have access to that forecast. And so, you know, these aspects of having a model that's always stable and up and running, doesn't crash the system ever, and executes in a timely manner so that the forecast information can get out to people to react to, really becomes, you know, very paramount goals in addition to making sure the model is also accurate. So again, compromises get made and get sort of baked into the process here, and it's a constant effort to try to harmonize all of these requirements together. Okay, so here's our main modeling ecosystem as it exists. What you'll see here is a number of different components that comprise the entire national water modeling system. And only the stuff in the lower left-hand box, those elements in the lower left-hand box, are the physical components of the model. The other components surrounding that box support the model in different ways. So there is this meteorological forcing engine, which is in the upper left-hand corner. There's a number of geospatial data processing tools, sort of the GIS foundational data sets that go into the model. That's channel networks, land cover types, soil type, a lot of parameters associated with all of those have to be processed. There is, in the National Water Model now, a fairly simplistic streamflow data assimilation method, which ingests real-time streamflow data from the USGS. And then on the output sides of the model, we have a suite of model calibration and evaluation tools. that support each model version development, and then, of course, web mapping services largely provided by the NOAA Office of Water Prediction and River Forecast Centers for forecast communication and display. So the scientific aspects of this really sort of focus a bit more on the model physics, the model structure, a lot of those input data sets that we talked about, and then how we calibrate and regionalize model parameters. The model, when it's running in operations, is not a one single model that spans, say, all time scales. It's the same modeling architecture, which is this WRF hydro architecture with a certain set of model physics and spatial resolution options. But then the configurations vary according to the different time scales of the forecasts that we're using. And that's to try to provide some level of optimization or tailoring for those different implementations. So there's an analysis cycle of the model, which has several different look back periods to try and capture as much observational data as we can get, both from streamflow and from meteorological data, and get those into the analysis cycles of the model. Then there's a short range forecast, which uses very high resolution meteorological data from an atmospheric model we'll talk about. And that produces 18 to 24-hour forecasts, depending on which hour of the day it's being launched from. And then there's a medium range forecast, which goes out to 10 days. It uses a coarser resolution global weather model as its forcing data set. And then a long range 30-day forecast, which is also an ensemble forecast, which uses yet a different global numerical weather prediction model. So it's these configurations and the different data sets that go into them, which is going to be what we're going to spend some time talking about today. I'll also note that our outside of CONUS domains for Hawaii, as well as Puerto Rico and the Virgin Islands, uses another set of model data that goes into it. And so when people are looking at forecast skill in different areas and ascertaining whether or not we've got good forecasts or bad forecasts or a good analysis, definitely is important to make sure you understand which forcing data set is associated with the configuration or the forecast that you're looking at. Okay, so again, we're going to spend a bit of time here now, probably the next 15, 20 minutes, talking about this forcing engine side of the National Water Modeling System. So this is really something to put together for reference to drive home the point of all of the different meteorological data sets which are being ingested into the model. So we have these broken out by model configuration. So we have the data sets that we use for long-term retrospective runs. These are these sort of 25-year runs and calibration and benchmarking. The reason we use these data sets for calibration and benchmarking as opposed to the operational data sets is just the simple fact that these other data sets are the ones that we have long enough time series for to help constrain model parameter estimates. And so there's been two different data sets that we've used over the past several years. We've started with NLDAS all the way up through version 2 of the model. And then this last year, we've been using this data set called the Analysis of Record Recalibration data set, which was generated by the NOAA Office of Water Prediction. And we'll be using that moving forward for calibrating the model and for these long-term retrospective runs. Moving into the analysis or the operational cycles, then again, we've got the analysis and assimilation cycle. It's ingesting MRMS, multi-radar, multi-sensor data that's produced by the Severe Storms Lab. We use both their radar only and gauge corrected data sets, depending on sort of how long we're looking back into the past period. And that gets blended with numerical weather prediction data, as well as River Forecast Center rainfall analyses for sort of these longer look back periods. So there's 4 different precipitation data sets, which are sort of blended in different ways and go into the analysis and assimilation cycle, depending on exactly where one is in the country and what period of look back you're looking at. For the non-precipitation data sets for the analysis and assimilation cycle, we are using strictly numerical weather prediction model data. The short range forecast, which is the one that goes out to about 18 to 24 hours, uses the high resolution rapid refresh, or HER and RAP models over the CONUS domains. And there is now going to be some bias correction applied to those in addition to the regridding and downscaling that goes on. Medium range forecast, again, is driven by a global modeling system called the GFS. That model, as many folks know, is now a 13-kilometer global atmospheric model based on the FV3 finite volume dynamical core developed by GFDL, the Princeton laboratory area. And so that is a data set that we grab operationally. We perform some downscaling to it as well as some bias correction before it goes into the medium range forecast. And then the long range forecast uses the climate forecasting system, which is run operationally by NOAA as well. It has a native resolution of around 50 kilometers. So quite a bit of adjustment is applied to that model before it goes into the National Water Model. So let's start looking at some of the configurations of the forcing engine. What you're looking at here is just a little bit of a buffet of different images that come out of the forcing engine or go into the forcing engine. Up in the left-hand corner, you can see an RQI, or a radar quality index, from the MRMS or the NEXRAD radar network, which feeds into the model. That gets blended with models to produce a final analysis product. You can see in that second panel, we're starting to ingest some of the microphysical information that's coming out of the MRMS product suite, as well as some of the meteorological models. So future versions of the National Water Model will actually have explicit precipitation typing associated with those. There's the non-precipitation data sets, so incoming long-wave radiation, air temperature, shortwave radiation, and so on. And so we'll look at how these get derived here. So this is our basic process that's used in the meteorological forcing engine. So this is generalized across all of the configurations, and there are some universal components that exist for all of the configurations. And then there's some configuration-specific components that have to be developed. Now, this forcing engine was recently, over the last year and a half, recoded to be entirely in Python using Python X-Array. So we're in the process of trying to get that onboarded onto NOAA's supercomputer. And prior to this, it was sort of a mishmash of NCL code, bash scripts, Fortran code, and was a little bit brittle and sort of difficult to sustain. And so we sort of bit the bullet over the last year and converted everything over to a comprehensive Python engine. So the basic format is that there's the data ingest components, there's formatting and time synchronization that has to go on. And then there are the basic processing steps, which include regridding down to the 1 kilometer scale of the forcing data for the water model, the downscaling that might occur with that. That is sort of applying spatial resolution or terrain specific corrections to the data to account for physical processes. Then there's a basic statistical bias correction to account for just bias and errors in the forcing data. And then we go through a product layering step to blend different products together to, say, fill the model domain out or to cover gaps in the data set in the case of the radars. And then finally, everything gets output as a standardized CF compliant netCDF file. So we'll step through these flow charts here in each of these configurations to see what's involved. Now, I'm not going to belabor each one of these and go through all of the details. They'll be here for your reference, but you'll see several of the components which feed into this and the steps that are taken. So say for our retrospective configurations with the forcing engine, you can see some of the source data sets. They go through a regridding step, they go through a downscaling step, a layering and contingency step to fill out the model domain, and then the final hourly output. A little science sidebar here then, as we've switched recently from using the NLDAS data set to the AORC data set, it's important to recognize that these data sets do have some very significant differences between them, and that leads to different model behavior and also to different calibrations of the model. This is just a quick snapshot of the difference in precipitation, mean precipitation, from those two different products. You can see it's averaged over the same period here. Looking across the CONUS maps on top, it's a little hard to see the difference because the gradients in precipitation dominate the color scale, but the difference is shown in the upper right-hand corner really highlight where we have a lot of sort of region-wide differences. And you can see, looking through the Appalachians, as well as in parts of the Pacific Northwest, where the differences between the AORC data set being the positive changes there and the negative changes being where an LDAS is greater, get expressed. And so there's a lot of heterogeneity throughout the mountains in the Western US, particularly in the interior, where there's trade-offs between those two different products and which one tends to have a little bit higher estimate or not. And then there's other regions where it just looks like the AORC data set might be a little bit wetter. Looking down at the bottom is sort of an independent verification against a network of meteorological station data that NOAA has. And basically where you see the yellows to very light orange and light greens are virtually sort of unbiased with respect to the observations, and the presence of reds show that the product, the AORC or an LDAS, has a little more positive bias. So there's some areas that appear to have a little bit more of a positive bias, but there's also a lot of areas mixed in with some negative biases. And so this creates a lot of complexity in being able to use these data sets, but at least we document these changes. Moving ahead, let's see, there we go, to the analysis and assimilation configuration. Again, not going to go through all the details of this, but suffice it to say, there's quite a bit of blending of data sets from MRMS, HER, and RAP that go into this. There's some filtering of the data sets, particularly at MRMS, where the radar quality is not so good, particularly at different times of the year and in different areas in the country. So we'll look at what that means. Here's a shot of a native MRMS dual polarization quantitative precipitation estimate product that's produced. And you can see here, when they essentially screen the data for radar quality and then produce the precipitation estimates after that, they end up leaving a lot of areas which have low or no precipitation estimate because the radar beams are blocked, the beams are too high, so on and so forth. This is actually a precipitation accumulation map that was created by NSSL for November of 2019. And you can see a lot of artifact behavior from the radars themselves, some beam lines and things like that. So all of this points to the need to really be blending this data with other sources of information. So we do this already in the current versions with the HER model, but NSSL has gone through a pretty major job to improve upon that process and add some other features to it. And the new product that they're going to be pushing into operations fairly soon here, version 12 of MRMS, looks something like this. This is essentially the same forecast or the same integration period of November of 2019, but quite a different change in the coverage of the service and in the precipitation amounts and the removal of a lot of those artifacts. And we're really excited to try this in the National Water Model when it becomes sort of available in its pre-operational state, and compare it with some of the existing blending that we do. They've got some cold precipitation threshold corrections in here and some other features which we think will be a lot more beneficial, particularly again for precipitation in cold mountain environments where there's sort of rapidly changing freezing levels and things of that nature. Another activity that's going on related to this with the MRMS group and NSSL is they're now producing a precipitation type product. And we're just starting to test this in the National Water Model in some experimental modes, and predominantly right now focusing on just liquid versus frozen partitioning and the hydrometeor types coming into the model. The current and past versions of the model use essentially a temperature gradient method for rain snow partitioning, which exists within the water model itself or within the NOAA MP land surface model. And we're going to be switching to using the information coming from the MRMS radar product as well as the NWP models to handle that precipitation type discrimination, as opposed to doing it in a hardwired way in the model. So we've definitely seen some initial sensitivities to this that look to be beneficial, and we'll continue to press forward with it. But again, for mountain environments, this is another critical behavior aspect of these forcing data that we need to get right. And clearly there's a lot of room for additional verification and probably improvement in these areas. Moving on then, this is just the graphic for short range. Again, we won't go through all the details, but I'll show some examples of what the downscaling looks like. The HER model, if we use in the short range meteorological forcing. It has a native resolution of 3 kilometers, so we apply a little more downscaling to this to get it down to 1 kilometer, and you can see a lot of the terrain structure pop out with respect to temperature, humidity values. We do a downscaling of incoming shortwave radiation to correct for slope and aspect. This is really important in mountain environments, as many folks know, but particularly for the snowmelt driven processes. We'll talk a little bit more about the snowmelt model later on, but it is an energy sort of radiation based approach. It's not a simple temperature index model. So getting the right radiation loading on the model grid cells where snow exists is really important. And so we try and pay attention to doing this radiation downscaling as well. You can see the impact of that in the Western US at low sun angles. There you can see the imprint of the terrain. This is a precipitation map, so it's highly sort of spotty and heterogeneous. And then another feature that we'll highlight in many of these forcing data sets, you can see the presence there of 2 different resolutions and some hard boundaries. And that's where we're blending data from 2 different atmospheric models, in this case, HRRR and RAP, which have very different resolutions. So HRRR, again, has a resolution of 3 kilometers, and RAP has a resolution of 12 kilometers. And so you'll see some hard boundaries there and some discontinuities. And those may, at some times, express themselves into different model fields. What you're looking at here is wind, but it's also present in several of the other variables. The medium range, again, there's the workflow for it. We do apply a mountain mapper terrain adjustment to the precipitation downscaling here, in addition to the other topographic downscaling for temperature, humidity, pressure, and solar radiation. This graphic just again highlights the difference you get between the sort of the before on the left and after the downscaling on the right for 2-meter air temperature. Lastly, the configuration for the long range model it's a lot more complicated than the other ones because there's a lot more what I would call a robust climatological bias correction that we apply in the long range configuration. This was some methods that were developed by Andy Wood and Andy Newman at NCAR based on some work using the long-term CFS reforecast data and the long-term INLDAS retrospective data sets. And so when you've got these operational models, meteorological models, when they actually have a long reforecast period associated with them, you can create these more robust bias corrections through things like quantile mapping, which is what's being done here, or CDF matching for a lot of the different variables. Don't have time to go into a lot of the details of this, but suffice it to say, this is how we translate data from the coarse resolution CFS model into the water model and its sort of high resolution implementation. Okay, so I want to pivot quickly then and talk about some other aspects of bias correction which are also being worked on. And these are for some of the shorter range forecasts, particularly the short range configuration, the medium range configuration. So over the last couple of years, we've tried to pull out as much station data as we can find to provide statistical bias correction to our already sort of downscaled meteorological data coming from HRRR, from RAP, and from GFS. And so we're focusing first on some of the non-precipitation data sets, mainly because it's easier to do. And with the shorter data set from the current operational versions of these models, you get a sort of a more homogeneous statistics batch using these non-precipitation forcing data sets. Challenges. And so what I'm showing here is some work that Joe Grimm and Yangxing Zhang have been working on at NCAR, trying to develop temperature corrections. And when they went to go look at this, they found that there are biases that are systematic, not only with respect to region across the country, but also with respect to lead time, the diurnal cycle, and the seasonal cycle. So each one of those behaviors is sort of gets regressed out of the model in this bias correction procedure. The maps here just show at different lead times some of the different biases according to comparison with station data that was created. And so what you'll see here is some of these correction functions that we're applying to the model. This is an example of the correction that's applied to the model straight as a function of lead time, where the black line is the actual bias, and the orange line here is the functional form of the bias correction that we're applying. This is the same thing, but for the changes in the bias associated with the diurnal cycle. So in this case, we're fitting a sine curve to the data You know, these temperature departures here are on the order of, you know, fractions of a degree in the aggregate across the country, but in some local locations, they do tend to be a little bit greater. And then for seasonal cycle, the same kind of thing, where this particular model, the HER model, tended to have a warm bias on average in the summertime, but a colder bias in the wintertime. And so obviously we would want to account for some of that systematic seasonal bias throughout the year. Shortwave radiation is another variable that's been sort of identified as having some biases associated with it. Like temperature, this can have some fairly significant impacts on snowpack ablation rates and energy-driven processes in the model of evapotranspiration. And so working with the HER group, you know, we were able to sort of track and identify how the bias in shortwave radiation was occurring in the prior version of HER and now in the current version that's becoming operational. And we can go and develop some bias corrections for that. So what you see here on the left-hand side is a diurnal cycle of the incoming shortwave bias as measured by stations on the ground. And a lot of these come from either the NOAA Climate Reference Network or ARM sites, the DOE ARM sites, where we have good radiation measurements that are kept. And you tend to see this fairly significant daytime bias in the HER model at these particular locations. And that is a bias of up to 60 watts per square meter, which is, you know, of a magnitude similar to some of the dust or impurity forcings on snowpack in some conditions. And so this is certainly something we want to be aware of and provide some correction for. And so you can see there's a functional form now which has been developed and is going to get applied into that. And of course, these results are all shared back with the HER team, and they can take these into consideration as they look at their future improvements. And I know this has been a variable which has been on their radar for some time as well. Long wave downward radiation, similar. This one doesn't tend to have quite as strong as a diurnal cycle associated with it. And so in this case, we're applying just a straight 9 watts per square meter adjustment at all times. And in fact, the long wave radiation here is a little bit low. And you could come up with a hypothesis that if the shortwave bias is high and the long wave is low, there might be a little deficiency in some of the cloud cover associated with that. We're not getting into all those details here, but we're just looking at these components of forcing variables that are coming into the model and making sure they're as good as we can make them before they get into the hydrologic model. Okay, so that is essentially, in a nutshell, what we've been doing with these forcing variables. And really the last, I say, year and a half has been this focus on retooling and rebuilding this forcing engine to be able to have all these capabilities with it. Now it's in a Python mode, which is a lot cleaner sort of software to do. And so we're hoping to sort of wrap up the development of this within the next couple months and work on the documentation and then release this to the community as part of this overall suite of tools. So folks, if they want to, can start to experiment with some of their own methods for doing a lot of this work, or maybe even using some of their own data sets. So then I'm going to pivot now to looking at some other aspects of sort of model performance, and we'll focus a little bit of this on sort of what the model's doing in certain mountain environments. So the goal here is, you know, we're trying to represent a host of these different hydrologic processes with some fidelity so that they can be used for a lot of different applications beyond just stream flow forecasting. Our little graphic here is our typical hydrologic cycle and sort of process schematic. And when we go into the WRF hydro modeling architecture, we've got a lot of options that exist for representing these processes in the model. So this slide is again in here as a reference for folks so that you can see what are the different options that exist within the WRF hydro system. And then on the far right-hand side, which of those options we actually use in the National Water Model configuration. So for the column land surface physics, which handle the energy and water exchange with the atmosphere, on the land surface, it's the NOAA MP land surface scheme. We do diffusive wave overland flow routing at a 250 meter grid, 250 meter routing of saturated subsurface flow. There's a conceptual base flow model. We do Muskingum-Kunj channel routing. It's just a hydrologic as opposed to hydraulic routing methodology within the NHD plus vectorized network, and some simple reservoir treatment in the current version of the model. So this land surface scheme, NOAA MP, is really where sort of the rubber meets the road in terms of how the model is going to perform and take those forcings that we talked about and generate either hydrologic state variables or runoff terms that end up in our rivers and streams. And so this is a schematic of the NOAA MP model. It is a sort of a full energy balance model. It's got a multi-layer snowpack scheme, which I'll show a little bit more on in the next slides, multi-layer soil moisture scheme, an explicit canopy associated with it, and of course with all this, a host of model parameters which have to be estimated or calibrated and regionalized. There's a lot of literature on the NOAA MP land surface scheme. These are sort of the seminal papers that were developed by Zongliang Yang and Guiyou Nu back in 2011, but there's been a lot of development since this period. As we've gotten the model and used it in the National Water Model, it's evolved a lot as well. So I want to dig into the snow for a little bit because I think it's relevant for a mountain meteorological community to have an understanding of what the snowpack model is. As you can see here, the different processes related to snow are contained within a number of different modules within the NOAA MP scheme. So there is a multi-layer snowpack formulation in there. It handles new snow and its treatment associated with density and albedo. We can have snow that exists in the canopy or sheds off the canopy. There's a snow-covered fraction or sort of a snow depletion curve relationship which exists within the model, and that's of course a large source of uncertainty and tuning. It is a full energy balance radiative exchange model. It has some simplicities, of course. It's not the current version with 2 different bands of radiation, but as opposed to a broader number of channels. But it does surface energy flux, it's thermal diffusion through the snowpack and sort of carrying of meltwater temperature, and has some aspects of compaction associated with it. So there's a wide spectrum of snow models out there, which vary in their complexity. I would say this is a moderate complexity. There's certainly a lot more complex schemes that could be used, but it's what we've been using for the last several versions. We analyze the model in a number of different ways. What I'm going to show you now is some regional behavior and some sensitivity tests we did when we switched from a simple snow aging scheme that came from the class model to this 2-channel snow albedo scheme, which is adapted from the BATS land surface scheme, and some of the sensitivities. And so what you're looking at here are just essentially some SWE curves throughout the wintertime, averaged over that inset model domain, with the SNODAS as the reference here. So the operational SNODAS product, which is generated by the No-Risk folks in Chanhassen, Minnesota, and a couple of different National Water Model experimental configurations. And for this particular area of the Central Rockies, you'll see that the model does tend to be low. We're going to look at different years here as we sort of toggle through. And I would say by and large, those low biases appear to be mostly related to some accumulation versus ablation biases, meaning that we sort of depart a little bit more and more throughout the year all the way up to peak, and then things sort of ablate at a similar rate in the springtime. Switching areas to the Pacific Northwest, this appears to be a little more pronounced. This is just one simulation year, 2011. We will see a lot of variations from year to year in how the model performs. That's 2012. Again, quite a low bias. In 2013, it's low, but then go to 2014 and it's fairly similar. The attribution of those biases about why we're getting such a big departure in some of these mountain areas is not super well known yet. It's not known if, say, more of this precipitation is falling as rain versus snow in the model during these areas, or if it's just a low precipitation bias during those years as well. And so that's something that still needs to be dug into, and it's one of those things which definitely varies from region to region. Toggling ahead, this is going to be, say, the Central Rockies, sort of northern Wyoming, southern Montana, far eastern Idaho. You can see some of these curves again. The variations between the model runs tend to bounce around quite a bit too, but this particular area doesn't seem to have too bad of a pervasive bias, despite a lot of variability. Now, SNODAS is certainly not truth. We know that, but in terms of a spatially distributed snow estimate, it's one of the probably the better products that we have available to us. It's obviously a NOAA flagship product, and so It's one of the things we use. We also compare against SNOWTEL, and so the two scatter plot graphics you see on the right are really sort of a kitchen sink dump of all sites, all times SNOWTEL data versus the water model. And we're looking at two different versions going from version 1.2 to 2.0. And what you see there is that the model tends to be low bias with respect to SNOWTEL, but that bias has improved or gotten a little bit less from version 1.2 to 2. Now, whether or not one might argue about the spatial representativeness of a SNOWTEL site and is it overestimating because it's a classic hole in the forest, or whether it is the best thing to use or not is a whole other topic for discussion, but needless to say, it's another metric that we track. In the center there, those lower two panels, we've also been doing some work in comparing National Water Model outputs with ASO data lately, or the NASA Airborne Snow Observatory data, since it's giving us probably some of the highest quality spatial depictions of snow depth that we've ever had. And while it's isolated in space and time, it's certainly a valuable tool for analyzing these data sets. So moving ahead, we'll just wrap up with some estimates of stream flow. This is just a reference plot for the fact that we go through this sort of detailed calibration process and we track the performance of the model with a number of different model metrics, about 15 different model metrics at any time. And we track the parameter changes as we go through that iteration. So I'm not going to get into the details of that, but then talk about what some of the end results of that. And so what you're looking at here are histograms of percent bias in stream flow all across the country, and then the map of that in the lower left-hand corner. And this is for all USGS stream flow gauges. And blue is high bias, red is low bias, yellow is relatively unbiased. So in the histograms, we've seen some nice convergence of things towards, say, the central tendency of the model over time, and that's been great to see. But there's still some pervasive areas of particularly rather high bias, and those exist throughout the high plains in the western US. If we look at just the Gauges 2 data set from the USGS, or their unregulated, sort of high quality, long period of record data set, which is much thinner, so much fewer sites, you do see that the model does tend to perform a lot better in those cases, and those pervasive high biases tend to go away. And the reason for that is really the impact of water management on essentially the verification here. The model has essentially little to no information of water management in it as it's generating this forecast. It's got these passive reservoirs in it. And so downstream of significant water management operations, whether they be large reservoirs, diversions, interbasin transfers, you're going to have some sacrifices in performance. And clearly the lack of withdrawals of coming out of western rivers is a major influence on that. Now, in the next version of the model coming out, version 2.1, there's a big push made by the Office of Water Prediction to ingest operational water management information. And so we're hoping to see some significant improvements related to this. But for folks in the West, this is definitely something to be aware of. Different metric here, same idea though. We're looking at Pearson correlation. Up along the top is how that distribution or histogram has changed over time. Things have shifted way to the right. In the lower left, you've got the national panel of that, where you have light colors, you have very low correlation, the darker colors are the higher correlation. This is for all of the USGS stream gauges. If you go to just the Gauges 2 reference basins, it looks like this. So the high plains, the desert Southwest, and even the mountainous areas within the desert Southwest tend to be some of our more problematic areas. Our headwater areas throughout the West tend to perform a little bit better with respect to bias and correlation, but there's still definitely room for improvement in those areas. Looking at, again, the same metrics, but in a just sort of a continuous regionalized map, you can see these differences. So on the left-hand side, we've got percent bias from all gauges and reference gauges, and you can see on the bottom, there's a lot more yellow, which is what we like to see. That's our central tendency for percent bias. And then on the right-hand side, as we go from the all gauges to the reference gauges, not as big of a difference here, but you do see some differences that pop up in these areas for correlation. Another metric that we track is KGE, or the clean Gupta efficiency. It's just sort of a combined metric for looking at different types of hydrologic skill. And here you can see that we have some areas where the clean Gupta efficiency tends to get better as we go to the reference gauges, particularly in the Pacific Northwest, throughout the Appalachians. Central Rockies is a little bit better, but a bit of a wash. And then sort of the high plains is a pervasive area of lower model performance. Okay, there's a host of other variables that come out of the model we don't really have time to get into today, but I'll just mention that they're there. Things like soil moisture, depth to saturation, evapotranspiration, surface overland flow, channel flow velocity also is a variable that's predicted by the model. Not much information on verifying that at this point in time. I'd say it's pretty uncertain, but we see some relative changes for channel flow velocities, particularly in our higher gradient systems that would be interesting to look at. We do look at soil moisture evaluations. We compare modeled soil moisture with, say, information from the SCAN network of soil moisture observations. And one of the things you'll notice is something that's kind of common from a lot of these models is the models tend to have less variability than observations do. And whether that's a sampling, an instrumentation issue, or a model formulation issue, I think is open to discussion. But it's one of the things you'll see, particularly as you get to the lower and lower soil profiles, you see a lot less dynamics than what you see in a real system. These are just some examples from the Pacific Northwest from a couple of days ago, where we've got some fairly wet conditions. And in the upper left-hand corner is a map of depth to saturation. So anywhere you see a yellow pixel there, the water is essentially at the surface and the soil column is fully saturated, and that organizes in, say, the valley bottom areas. And those tend to be associated with areas where we have, say, significant amounts of water that are sort of ponding on the surface or flowing around as overland flow. So the model's sort of capturing that downslope redistribution and organization and runoff production. And just some other examples of this in some different areas of the country. So with that, I'm going to start to wrap up. One of the questions we get from folks is there a long-term retrospective of the model that is available? Excuse me. And the answer to that is yes. This is just an example. So for each version of the model, we've been putting out a 25-year simulation of the model using either NLDAS or the now moving to this AORC data set. All of that data is available on Amazon Web Services and Google Cloud. I think it's also available on Microsoft and the OCC Consortium Cloud, as well as through NOAA's Big Data Services. And so for folks wanting to look at some long-term simulation behavior of the model or use it for other kinds of, say, hydrologic analyses or drought studies, that data is freely available, and we make that available. Web services around the efficient processing of that data are not necessarily available, so user beware. But all the variables that I've shown here are available through that, and these can be really useful data sets for understanding where the model does reasonably well when forced with good meteorology and where it doesn't. Keep in mind, though, that is different than what's in operations, because in operations we do use different meteorological data sets. So a number of different things coming up. We're working on version 3, as I already mentioned. I'm just going to hit a couple highlights. There's a lot of work going on with coupling with the coastal zone and coastal models, which we'll see moving forward. But more relevant to this mountain meteorological community is that we're starting to embark on an implementation in Alaska, and we're starting with that yellow box in south central Alaska, the Cook Inlet, Copper River basins, and working with the Alaska Pacific River Forecast Center and the USGS in the implementation in those areas. And so there's going to be some physics changes coming up with that, handle some of the braided river systems, some aspects of glacier dynamics, glacial melt into those systems. And it's going to be a really nice opportunity, I think, for both a lot of research and changes in operational prediction. To that effect, we've just been wrapping up a project that uses the WRF hydro system in Norway to look at some glacial melt. In this particular case, I'm not going to go into the details here, but we had some fairly well detailed measurements of glacier depth and snow measurements on a glacier in south central Norway. And so we adapted the Crocus model to work in sort of companion with the NOAA MP land surface scheme to represent some of those glacier processes, not really the flowing aspects of the glacier, but just sort of the standing thermodynamics and melt along the periphery. And this is what we'll be doing using as an initial implementation in Alaska. So with that, I'll leave this as the last slide for folks wanting a lot of more detail related to either the National Water Model or particular the underlying sort of WRF hydro model structure, training materials, test data sets, Jupyter notebooks, things like that. We offer a ton of that material through our WRF hydro website. And so feel free to browse. And if you're interested, get in touch with us about that. Other than that, I will go ahead and stop there and any questions. So Ethan, back to you.
Thank you very much. And thanks for a tremendous talk. That was a lot of information. Before I take questions, I want to remind people that we have a upcoming Mountain Met meeting July 13th to 17th in Park City. Abstracts for that are due March 12th. And so it's coming up real soon. If anybody else has questions, you should be able to unmute yourself. Feel free to go ahead and do that or you can type something in the chat box. As people are working on that, I just want to thank Dave once again and ask if you can maybe mention some of the observations that are brought into the National Water Model, because you mentioned having this sort of analysis spin-up period, because I think that's a little different in a model like National Water Model than it is in an atmospheric model, and that might be a nice point for people.
Yeah, that's a great question. I would say, if we talk about the ingest of observations into the model as a data assimilation exercise, very little is really assimilated into the National Water Model right now. Only real-time USGS streamflow data and the associated data which makes it into these meteorological data sets. So we're not yet assimilating things like snowpack or soil moisture, or even things like green vegetation fraction and stuff like that into the model at this point in time. There's a lot of research going on in that area, and there's a lot of infrastructure development to build those data assimilation tools. But operationally right now, beyond just the meteorological data and the real-time streamflow data, real-time observation data isn't getting into the forecast. It's only used on the evaluation side.
Thanks. Any other questions? So Justin Minder says, with regards to snow albedo, is there any representation of impurities in snow? And if not, are there any plans to incorporate this in the future?
Yeah, great question. Thanks, Justin. At this point in time, no, not explicit representation of impurities. So when we switched from the class snow aging scheme to the BAT scheme, we did pick up the ability to have, say, this 2-channel, essentially broadband visible and near infrared parts of the solar radiation spectrum coming in, and have the ability to track albedo in those 2 channels. Now, one of those is proportionately more related to the age of the snow in terms of crystal morphology, and one of those bands would be more applicable to impurities. The problem that we get to is that right now we don't have a sort of prognostic impurity component in the layering scheme of the NOAA MP model that is sort of getting dust or other impurities deposited on the snow and then emerging as the snowpack ablates. That is something that is tricky to do. Other models certainly do, and I think it would be an interesting thing to start to look at. But lacking that, I think there is opportunity to, say, look at some aspects of assimilating some other snow albedo products, say from MODIS or ModScag or ASO or some of these other things that might end up being able to better constrain what the model's using as its albedo formulation.
Thanks. And another question from Y Ma saying, large bias exists in model performance for soil moisture in the first layer. Would you give some explanation? Thanks.
Sure. Well, that was just one particular site. Across the entire model domain, I would say the soil moisture changes in a lot of different areas. The soil moisture behavior and the soil moisture validation changes in a lot of different areas. I would say the lowest layers tend to have the most bias in them towards the bottom. Again, we also have that lack of dynamics. The top layers tend to be more responsive to biases in the forcing data sets, in particular the precipitation data. So where we have, dry biases in the meteorological forcings, we're probably going to end up having dry biases in the near surface soil moisture. So there's been a few different focused projects on this, in addition to just the broad scale national analysis. And what we tend to focus on a little bit more with soil moisture is anomaly correlation and tracking the differences between that, because of the representativeness issue related to specific soil measurements and what the model is going to see at, say, a 1 kilometer pixel. And the anomaly correlations, this is particularly some work done by Mimi Hughes and Bob Zamora and other folks at the NOAA Esrael lab. We're showing pretty good tracking in an anomaly space of what the model behavior was and sort of tracking variations in soil moisture. Bob Zamora did some additional work looking at sort of lowland versus upland comparisons, relative changes in the Russian River instrument network that he's got out in California, and found some pretty good behavior. But I will say in general, the model does tend to have a wet soil moisture bias associated with it. And the exact reasons for that, they relate to the fact that we're calibrating the model to stream flow, and we're not calibrating the model to soil moisture. So it sort of is the unwitting recipient of calibration of stream flow. And we're not yet sure exactly where the rest of this water should be going that was coming out of stream flow. Is it a positive bias in precipitation, or is it a lack of evapotranspiration that's leading to these wet soils? So it's kind of an open question.
Thanks. So maybe one last question. And before that, I want to mention to people, as I see people are starting to drop off, that the next mountain meteorology webinar will be Dave Whiteman on May 14th. And I'll send out email information about that a month prior, talking about ice mushrooms on summits in Patagonia. So last question comes from Vincent Vianney, asking, are you using information from a snow analysis product such as SNODAS, or is the snowpack scheme running in an open loop mode in your system?
Yeah, so it is currently running in an open loop mode in the operational national water model. Now we have a lot of discussions going on with the SNODAS developers about a long-term data assimilation framework and activity. And I think the long-term plan is to attempt to eventually unify these different kinds of tools together into one, flagship agency-based product. But we're not there yet, and it's going to be, I think, several years before we get there because there's just so much more work that needs to go into building a lot of that infrastructure for building that product into the model. So we use SNODAS really as a benchmark right now, as a means of comparison. The SNODAS product is the official snow analysis for the Weather Service, but it's certainly something we look at.
Great. Well, thank you very much, Dave. I don't want to take any more of your time since I know we're over our time. And thanks to everybody who tuned in for this. I'll have the recording on this posted in not too long, I hope. And again, a reminder to submit your abstracts for the upcoming Mountain Met meeting due March 12th. And the next webinar will be May 14th. Thank you very much, everyone.
Thanks, Brian.